Okay, you are now recorded.
Okay. Well, thank you for having me. So I hope to offer a practical introduction to the numerical bootstrap, get you all the participants going to find their first numerical bounds and to learn the concept involved and also the tools that we use in modern numerical bootstrap. Yeah. So hopefully by the end of the tutorial, you will be able to do to derive some non-trivial bounds, and you will at least be somewhat familiar with the tools used so that you can answer your own questions that you are interested in solving. So yeah, I will give a very quick recap of things that you already heard a few hours ago. So I think I don't need to be go into details since it's quite fresh. So central in the numerical bootstrap is a crossing equation. And given unitarity, we know that with followed by a function that is conformal cross ratios u and v, and that depends on the external dimension of. If here I'm assuming that we're considering a simple system with just one identical scalar operator, and then it has some dimension, and the crossing equations will depend on that, and also they will depend on these values delta and L of the operator that is exchanged in the OP between the two identical external operators. So we saw that you can think of this crossing function as a vector in the infinite dimensional vector space of u and v, and that the bootstrap consists of searching for a possible functional or equivalently for a separating plane where all these v's lie on one side, given a certain assumption of the spectrum. If that's the case, then you can exclude that spectrum. So we saw this kind of image that if given some spectrum, all the vectors cover the whole space and there is no separating plane, then you can't exclude a point. But if there is, you can. That's assumption for the CFT. And it does not give a valid conformal field theory. And yeah, and that depending on the spectrum, the ranges that get spanned by these vectors can change. So for instance, if you perhaps, like in this case where these vectors, maybe perhaps this vector is only there for a certain dimension under, for example, under some gap only for dimensions under smaller than 1/2, and then you might find that depending on whether you allow that in your spectrum or not, you can exclude a point or you cannot. So when you do numerics, this infinite vector space has to be reduced somehow to a finite vector. The simplest, most neat way that you can do this is just to evaluate this function at some grid of points. So for instance, you can say, let's do 0.51, 0.55, etc. And you will get some, yeah, you can construct a vector of these values, and this will be your reduced search space for a linear functional. So you're only considering a linear functional in a reduced space, so you might not find the most constraining thing. And as you increase the search space, your bound should get better and better. And yeah, we saw that what we do in practice is take derivatives instead of just evaluating it at some point, we take derivatives around a certain point. So you get sort of Taylor series. And yeah, you can see that often as you increase lambda, the bounds, so lambda, sorry. We often characterize the number of components of this functional search space by some number. So for instance, lambda gets used, and lambda means that you only include derivatives up to a total of that lambda. So you write them, I think, correctly. So you would only include a certain number of derivatives up to derivatives in one direction plus the other, n plus m equals some number. Okay. Anyway, and as you increase the search space, your bound should get stronger, but a point that is excluded will remain excluded because you just found a functional that is positive. So in order to construct such a vector of derivatives, you need to compute, well, the derivatives of conformal blocks, because what is this function f? It's just a combination of conformal blocks times some factor of the cross ratio. Computed, and as you go include more and more components, you will have to be more efficient about doing this. Sorry, is there a question, or is this just some noise? I think there's no question. So there are some tools to do this compute this efficiently. We will, during this tutorial, know some of the important tools. So similarly, this spectrum, which are like all, is this continuous, a priori continuous unknown values of delta, pairs delta and L, and also, of course, if you have global symmetry, some global symmetry label. But for simplicity, we just consider singlets. And you have to represent this enumerated by some finite amount of information. So the naive approach, again, is to just discretize. So you say, well, instead of including continuously the whole interval, for instance, above some gap, some value, we say we just sample them, and we assume, as you can see, actually, that in the large delta limits, the function approaches some constant asymptotic value. So you can say, we only demand positivity on some. But in fact, and so we see in a simple example how this works in the problem sets that I hope you will solve. But a more rigorous method is also available, because it turns out that the kind of questions that we ask, where we ask positivity on these functions or these, well, vectors of functions, that you can phrase that as the question of positivity of a certain polynomial, for, say, x greater than 0. And such a problem is known to be that you can write it as a problem of finding positive semi-definite matrix. And so using the second approach, you find that you have to solve a semi-definite program. And again, there is, and it turns out that in order to do this, well, you have to also use, inherent in the Bootstrap is certain cancellation that requires high precision. And so a dedicated tool called STPB was developed for this. And so one of the things we will do is also look at that, how to install it, how to use it. And the first example, this first exercise set that I propose you to do, I have tried, the example is self-contained in Mathematica. You only need Mathematica, and yeah, it will be able to get your first bound. So we will be using this first method of discretization, for example, and linear programming. even though that's not the most rigorous thing, because it will already introduce some of the concepts that you need to know. And then we can start by focusing on this conceptual part and not only installing things. And then I propose that in a second exercise set, we will focus more on getting close to the real workflow as used in modern conformal bootstrap. Yeah, similarly, besides this question of whether point is, so when I talk about point, I'm saying, for example, you want to see whether a certain gap to not have any operator below some value, let's say delta epsilon. As in the Ising model, you know that there has to be this operator at 1, and so if you, so normally you ask whether, let's say 0.5 is this for a given value of the external dimensions, delta phi is 0.05 allowed, or can we exclude it? And yeah, a lot of the bootstrap problems are posed like this, but there's also another way you can ask questions. For instance, you can optimize something so that you get a bound on an OP coefficient. So that's, for example, you find the central charge has to be below this value given these assumptions. Yeah, the central charge is related to OP coefficients through word identity, but in general for OP coefficients, you can do this. So yeah, we will also discuss in the future problem how to set up such a problem. And similarly, recently, together with Slava, Richkov, David, Simon Steffen, Ning Su, and Balt van Rees, we introduced the concept of navigator function, which offers a continuous measure of success. So it doesn't just tell you whether a point is allowed or disallowed. It also gives some measure of how far you are from the boundary between allowed and disallowed regions, and it gives you a way to efficiently find this boundary. So I will also in the end show you how to set up such a computation, which is similar to the computation where you find the bound on OP coefficients. So that's a bit of the plan of what we would like to do. Tutorial. Of course, the idea is that you will be doing these things yourself. I will guide you and have provided some files that will offer you step by step what you need to do. Such a way that afterwards you also know what to do if you want to do something slightly different, because of course that's the idea is that you really don't just are not just able to hit the button to let it run, but to understand if you would want to answer some other question, what you would do in that case. So yeah, please ask. Ask questions, interrupt me. It has been a bit silent, but I'm assuming that's just because everyone's muted, and that hopefully there are still some people.
I muted out the people who were not, but you can unmute yourself if you want to ask any questions.
Great, thank you. So indeed, if there's a question, ask, of course. And also, yeah, if you feel that there's something that is the most important thing to learn, like, well, for some things people already get to, but some things we might not. You might feel like the most important thing is this OPE bound, or you might find that the most important thing is just interpreting the result of the semi-definite programming solver, STPP, then please let me know. We can dedicate some time to that. Right. So at this point, I think that I would just, so I on Slack, sorry, I have to switch what I'm sharing. On Slack, I shared a notebook that contains the questions, but also at once immediately the solutions to some simple problems that will give you an intuition on why we can find a bound, how we can find it, how you can make it such that you can find automatically and without looking at plots. And but first we will start by visualizing some things that show why you can find the bound in the first place. And so at this point, I would say that I hope that the node.
Can I ask you, because I'm not 100% sure that everybody registered in the program is also looking Slack.
Okay.
So I don't know if there are among the people, because you are. I could download the file, Mathematica. I'm not sure if there are between the people who are following now. Everybody can access to this file. I just want to tell you that.
Thank you, and definitely let me know. I mean,
yeah.
But I think we can safely assume that if someone is unable to join even Slack, then that person has no chance to have any success with the numerical bootstrap. So they may just not bother.
Okay, welcome to the rational way of doing
It's like we have to introduce some first barrier, entry level.
Okay. I just put down the problem.
Okay.
Ok, thanks. Per questo te l'ho mandato, di come ti conosco.
I for one got the file, so I'm qualified. So
Great.
Go ahead and shoot.
Congratulations. So let me. Why is it not me to share? Oh, it does. Okay, sorry. So now you should be seeing Mathematica file. I think I'm sure if I'm sharing it correctly. So yeah, first I should say that I just edited that the tutorial is constructed from some examples that were already also previously available. So there is a tutorial by Miguel Paulos on which part of this is based. There's an example exercise in the lecture notes of David Simmons-Duffin, and Kay Weiss shared some files with me. And so most of the credit should go to these people. I'm just putting it together and presenting it. Right at the top of the file, I write the problems in terms of some in terms of some words, but I encourage you actually to just try to read along with the solution that is below, because I think that I think that a good way to learn here is to just look at some and try to understand why that step is made. And so let me go to a certain endpoint already, because I think it illustrates something that you would like to do. So for instance, in one example, sorry. Oh, oops. So this is not the best way to do it. You have to go through it. Sorry. That's sorry. I should have prepared things beforehand. Okay. So what I first suggest you do, what is the simplest you can do? Well, the simplest you can do is try to look at would be a one-dimensional vector space. You just evaluate f at some point and you see whether you can find a bound. You can find that you can't find a bound, because one component will be the component that you normalize on some vector, and you basically need to have at least two. So I consider a problem where you take some two-dimensional vector space. So you evaluate this function f at two different values of z and c bar, and you see what kind of values are spent by what kind of factors you get for different values of the internal operator that is exchanged, the one that is defined by delta and L. And find whether a bound could exist. So again, if we go back to the image where either the vectors all lie on one side of some plane or they don't. If you consider just a two-dimensional space, then this is basically a question whether whether in a 2D, so what we're asking is in a 2D plane whether vectors can add up to 0, and they can if their convex hull contains the identity. Alternatively, you can phrase it as if you just go to polar coordinates, if they cover like more than half of the space, more than pi worth of space, then you can use them to sum up to. If they don't, then you can't. And so what I show here is for some example where we just evaluate certain points. Okay, it's a clever combination, but okay. How these vectors look, just their polar angle, because that's the thing that matters for different values of delta and L. So here in orange, you see actually the value spent by the L equals 2 family. And okay, they covered this small part of the angles. And here you will see, ooh, I'm sorry. Perfectly. No. Okay, sorry.
In this manipulate widget, if you press on plus, I think you will have more control. There's this plus icon.
Right, that might be better. Okay, now it's doing annoying things because why? Okay, sorry. Let me just. But okay, it worked. But I think the dragging it was fine. So here I show the family, the L equals 0, the scalar family. That's so in color. The color is represented by. So what does it show? They show how as you increase delta, it moves like this, and then at some point it moves back. And we can see from this color chart that, yeah, somewhere around, you can't see it exactly, but 0.16 or something, we go past this, the furthest point that is, so we're assuming, for example, here, just that there definitely is this stress tensor, which is at this point. And there's this other, the rest of the family of the spin 2. And now the question is, what, depending on assumption on the scalar family of operators.
Sorry, I get really lost. Can you explain what we are doing?
Right.
Just because, thanks.
Right, maybe it's too fast. I also would say that I think it's maybe I was too fast in trying to go to do some.
Yeah. Go slow. No, don't worry. Go slow. There are people like me that need some slow.
Right. So we have this function f that let's just start at the very start. We have this function f, which is some function of a couple of things: the external dimension, the dimension of the operator that get exchanged. So, for example, in the Ising model, if you have the sigma, if the external operator would correspond to sigma, then you would have the sigma b would contain some operator epsilon, and that would be, for example, this with delta equals 1 and L equals 0. And you also have these variables z and zp because, yeah, even if you fix this to something, then it's still a function of these conformal cross ratios. So in this case, let's fix delta phi just to the Ising model value and look at some examples. So you get some function of z and z bar. Now we can say, let's just evaluate this also at some point. Sorry. We evaluate, we look for some, so we have this infinite dimensional vector space spanned by f for general values of z and z bar, or equivalently u and uv. These are just different conformal cross ratios, but they say the same thing basically. And so if you evaluate at some points, then for example, you get a vector with some numbers. And here we looked specifically at the case that the dimension of the exchange operator is 1 and the spin of the exchange operator is 0. And so this, so if you take,
here we're talking about a two-dimensional global conformal block, this one.
So yes, so f yeah. So here the function f crossing is what I showed before, is this object that is created by taking one conformal block and
okay, the two-dimensional is okay.
So in 2 dimensions, this has a compact form. This is the known expression, and it's easy to evaluate it in Mathematica. So yeah, we're considering 2D for that purpose.
Okay.
And so if you evaluate this for some operator, you get some vector, and we can take.
Okay, so the first entry is the external operator. The second entry is the internal channel. So one weight is like we are considering like 4 operators with dimension 1/8.
Right. So here I put 1/8. Yes.
And the second entry is the internal channel.
This is exactly the internal channel.
Belt. Okay.
So this is the dimension, and the third entry is the spin of it. So.
Okay. You are considering okay, but not only the conformal block, but the also the z bar. Okay, sure.
Sorry, these last entries are the z and z bar.
Okay, sure, yeah.
And so if let's say 2 points, then you get some. Oh, what did I do? Sorry, I replaced it back. So then you get some value. You just literally get the vector, and you can look. Take the vector, and you can say, let's look at.
Okay. So like just to be sure, like sorry if I am naive.
No, please ask questions.
When you put like f crossing of 1/8 x, for example, L = 1.
Yeah.
You are doing if I think about the global conformal block, you are doing the conformal block with internal dimension x0 times the conformal block with internal dimension x + 1 on the holomorphic part, and then you do you sum the.
No, sorry. I think that I confused you. Perhaps I mean, sorry. This was delta. Where we write. Okay, often we write. In most of the file, it's clear that it's delta and not x.
No. Yeah, I know. It's because being working always in 2D.
Yes.
I am mentally always thinking about the holomorphic and telomorphic part.
Okay.
Okay, so when I think about the conformal block, the internal channel has not a spin. The spin is like the difference between holomorphic and telomorphic dimension. Okay, so here you are, I mean, what when you mean delta L, you are considering the holomorphic and telomorphic conformal block, one associated to the dimension delta, one associated with dimension delta plus L, something like that.
Yeah, I have the opposite problem. So we have
I know, but
I think it,
well, Marten, since I know both languages, I can answer. It's delta minus L and delta plus L. H is equal to delta minus L and H bar is equal to delta plus L, and or perhaps delta minus L over 2 and delta plus L over 2. But we can look at the formulas. Martin, you can. Why don't you just point to the formulas defining this?
Okay. Sorry.
Because the formula is on the screen. F crossing equals.
Exactly.
G2G.
Oh, yes, yes. Okay, yeah, exactly. Cool.
And G2G is also equal. Everything is defined.
So the conformal block is some combination of these hypergeometric functions into 2D. And here I'm also assuming identical operators. And then you get this as this crossing equation.
Okay,
And,
I get it now. I get it. I understand.
okay. So yeah, if you evaluate it to two different values, then you will get some vector. And yeah, you get it since the only thing that matters is in order for the question of whether a separating plane exists, whether there is such a functional, only the angle actually matters. So it might be easiest to go to polar currents and only consider the angle. And so, for example, for this operator, you find that it corresponds to this angle. And if we take we go to the stress tensor. Sorry, then it corresponds to this angle. No, I did this. And so if you, so basically for every operator now in this truncated vector space, you can assign a angle. And so if you do that, you can look what angles get reached by different family operators. So maybe now this picture is a bit more clear, where if you take the L to be 2, or in your, well, okay, I will not translate it to your language, but you know, then for different values of delta, it will only reach these angles in this function, in some subspace of the functional set, the infinite subspace, that space that's spanned by vector space that's spanned by all values of Z and ZB. We restrict it to some two-dimensional vector space, and in that vector space, only these angles get reached, and the scalar family reaches some other angles, and we see that it goes up to a certain point and then it goes back. And the interesting thing to see here is that if there is no operator that has a dimension between, it has a dimension in this part where it goes like this and then back, then there is this separating plane, which, well, you can take it to go exactly after the stress tensor, that basically everything lies on the positive side of this plane, and thus you have found your functional that is positive on the whole spectrum. And so you find that there has to be an operator in this range. So yeah, the first exercise consists of trying to show this for some two-dimensional functional that you already find your first bound, because there has to be some operator of spin 0 here. Now, of course, here I say, didn't look what happens for the spin 4 and the spin 6 family. Maybe they are over here, and in that case, you would have no bounds because you don't need this operator in order to have cover enough in order to be able to sum back to sum them up to 0. But yeah, I encourage you to add those lines to this picture, and you will see that they lie in the same space that is already covered by the spin 2 family.
So what should we do? We should look at the file. We could we do the exercise 1, and then what do we like reconvene in 30 minutes, or what's the plan?
If you think that
Because
it can be
most likely we'll have more questions once we look at the file. Now
right.
it's hard to
I
formulate
definitely agree with that. So I would say indeed, like get started, ask me questions. I would say just ask me questions. I can leave it online. Ask me questions when you want to ask questions, and yeah.
Okay.
So for during the if you have get far enough and you have questions during this session, definitely ask me just live. And if you do the exercises later and you have questions, ask them on the channel, and then I can also answer them there. And people.
Well,
can
I
also...
guess what's not clear to me is that, okay, since you have this file and everything is already done in the file, so should we just like go through and run it step by step and understand what's happening, or should we write our own code?
Okay, I think that the easiest thing is to, well, not the easiest. I think that for me, a good method of learning would just be going through it and learning and understanding every step. But I actually also anticipated that some people would prefer to really come up with their whole code more individually. So I did at least a small write-up of the problems at the top, just where I just put some points of what you would like to explore. And so if you are more independent-minded, you can try to solve problems just from there, and then only look at solutions once you either are stuck or are done. So if you want to do it like that, then you can just only look at this. I think that it's already useful to go through it. And also sometimes I suggest, like, for example, here, I would suggest that you add to this plot the families, the missing families, so that, yeah, I mean, so that you can really see that those would not affect it. So for instance, add spin 4 and add spin 6. Mm-hmm. And so here and there, make some suggestions of what you can try to do differently, or yes.
Okay.
Sorry, Martin, one question on this plot. So if you press this little plus that Slava was mentioning, then you can put the value manually. Is this like the scalar dimension times 100?
Sorry, is this the scalar?
If you press the little plus there is you have the option of entering.
Right, I don't know exactly why. Because I did it a different. Okay, there was an issue that if you want to efficiently manipulate, I had to pre-compute the list because otherwise it was being laggy. So actually, the thing that you should enter there, I guess, is an index and not.
Okay, so it doesn't mean anything.
But again, I think that this is a small change. So okay, it's more an exercise in Mathematica, but you can also alter this, I think, quite easily. I think I just had to do this because when I really did it, that it was the dimension. Yeah, it got a bit late because then it has to, I think, recompute. But probably there's also a sufficient way, I mean, to do that. Or I can pre-compute them and index them per their dimension. But okay, so for now, yeah, it's just the index, so it's actually not that meaningful to look at the 80, but you can see here in the top up to where it is now. So up to here, we see that at 0.157, it's not yet reached this other side. I mean, that just so later that at around 1 point something, it goes past. And of course here it's color coded, so you can also look there.
So I have a question. In this example, what sets the dimensionality of the vector space is the number of points we are evaluating the
Yes.
conformal block on, is it?
Yes.
Okay.
So down to work, I guess.
Yes, good.
Martin, can I ask a question?
I'm replying without unmuting, of course.
So it's about naive attempt. It's not what you showed, but I was just going through the file now. The one with the two component functional. I guess you didn't show that. The one with the plot in which you show only the angular value and you just evaluate the scalar block. So what can you explain? What are we getting? Because here, so I see the red dot should be the identity, the angle at which the identity lies. So that's just 1 point. It's somehow like a little, in this parameterization is a little less than minus pi half. And then there is the line is the value, the angular position of in this two-dimensional plane of the scalar block. And it stays pretty much like at minus pi half until it rises rapidly, and then sort of it has some more fine shape. And so now, so since the identity is only 1 point, you conclude that at least one operator with delta greater than some value, which is more or less where the block rises, should be there. But is it correct to say that if I just consider, I mean, there's something here that you're not showing about all the rest of the blocks and all the rest of the spins? Because otherwise I would say that there's only one delta that for which the plane does not exist, right? For any delta which is not exactly separated by pi by the delta of the identity, you can find the plane, right? Either on one side or on the other.
You only assume one, yes, but as soon as you I mean, yeah, I agree. I mean, you have to cover like if you plot it again as a circle, then you have to have like, let's say 3 points that are well, which convex hull contains the center. So if you would just have 2 points, then
right. So you're saying there at least are two scalars here. Like one of them is bigger and the other is smaller, and then you would find you could sum up to 0, for instance.
Right.
I see. Okay.
Right. I mean, if you just have a sphere with only 2 operators, then it's unlikely, unless they are exactly like exactly at the opposite angles, they will not add up to.
Okay, I see. Thank you.
So yeah.
Hello, excuse me. Can I ask a question?
And unmuted. Yes, ask please.
Maybe it's naive, but in the part, the naive attempt at bound with two component functional there, the L here is angular momentum, right? Or the spin label. And in this plot, you plot the delta from L
Right.
to delta point split. I don't quite get it. Why it's bound? Why do you plot the range from L to delta point split?
Oh, sorry, it's slightly different. So okay, yeah. But why I plot from L to L plus 2, is that the question? Or sorry, is that, where is
Yes. Why is the lower bound? The lower range here is L, because I mean it's the same L with the spin label.
right? Right. So that's due to the unitarity bound. And actually, yeah, Slav pointed out that I might made a typo, but so yeah, I think that Alessandro didn't get to this yet, but in a unitary theory, the dimensions of the operators are bounded from below, and well, you can show this that by unitarity, if you look at certain correlators, that you can show that you can't have any operator below its own bound, and in the unitary bound are for integer spin. They say that you can't have any operator below.
Okay, yeah, that's actually from the unitary bound, right?
Right, right. So it's d minus L minus 2.
So what if we lose that bound? So if we don't consider the unitary bound, will we have something interesting below
right.
that L?
But so it's of course not. It's so yes, definitely the answer is. I mean, you can do that, but the problem is that the crossing that we are looking at. Well, for here it's fine. I mean, you can plot this and it would be something, would be a function. But if you want to do the trick that we want to do, where we say, if there is, if these vectors don't point like this, then they cannot add to 0. You want to find a separate plane. Key element to this is that this prefactor that you have in F, that this is positive, because if you can just add up with negative sign, then yeah, then this principle doesn't hold anymore. So basically, throughout this notebook, I will assume that you're looking at unitary theories.
Okay, thank you. That makes sense. Thank you.
Okay.
So one question is when people are willing to go a bit ahead.
Yes.
Well, I'm sure Martin will go ahead at any point, but
Sorry, your question is, I thought that you just had a question that is further ahead and you wanted to ask that, but.
well, okay, so I did the exercise myself of reading through the code until including the point that you showed. And this is more or less done now. So maybe other people have a similar impression that maybe we could resume. Any opinions? Well, I should have known this from a long teaching experience. I always have to formulate things so that if nobody answers, we just go ahead. Does anybody protest that Martin now goes ahead? Well, that doesn't appear to be the case. So please, Mr. Speaker.
Okay. Okay. I hope that people don't feel bullied by this approach of yours, but okay, I will continue. Is this still someone else sharing screen? Oh. Okay, so yeah, you're interested in moving on. You get this bound and you can see that this separating plane, which you can basically taking the position of the outmost operator, which is the stress tensor, that will define that is positive above some gap, and that we can exclude that there has to be an operator beneath that gap, so in this area. So you can verify that indeed that is the case. And then the next question would be, well, we don't want to, like, for every point start looking at the plot, seeing where it is. Okay, we can find the roots. That's sort of more automated, or like the root of, well, as I did here, you could subtract the outermost one and look for the roots, and in that place sort of automatically find bounds. But in order to get closer to where we just have some optimization algorithm, which either linear programming or semi-definite programming, that will just spit out the answer whether a function exists or not, doesn't exist. So to introduce this, I think it's easiest to first look at the exact bound that you already found and verify that you can find this in some automated way. And so we use here linear programming. And so you can look at, by selecting it and what linear programming exactly does. So normally you minimize some quantity, but here we're just be within the feasible set, given some constraints. We are just interested in finding any solution, so you can also just leave the quantity that you want to minimize. Just put zeros there, and we're just looking for any. Sorry, actually, when I opened the documentation, is that being shared? Maybe not, because.
I see what you discuss, all right. So
you see that I have here linear programming finds a vector X that minimizes the constant.
If you tried to find the documentation for that, I didn't see that. No.
Okay, so that's what I did. But okay, you can do that yourself. Also look at the documentation, see what it does. And so what does it do? It finds a vector x that minimizes the quantity c dot x, subject to the constraints m dot x greater than b. Okay, what does it mean? And x greater than 0. This will mean that we will look for a functional that is positive on some set of vectors. So we saw that we can evaluate this vector VH at some values of delta, and you get a numerical vector. And if you do this for some grid of points, then we would like to demand positivity on all of these resulting vectors. The grid of points should then, of course, be above some gap that you want to either, for which you want to test whether the problem is feasible or not, whether there exists a functional or whether there doesn't. So you can say, let's see whether, if you assume that there's no operator below 1.05. So in that case, you ask for positivity on some grid of values for delta and L above, with delta above 1.05. So starting from 1.05 and then some more. And you want to ask positive, if want to find some functional that's positive on this, and we don't care about optimizing something else while we do it. We just want to find any solution. And so we can do that by picking the second argument of linear programming to be some list of these vectors evaluated at various values for delta and L, and the objective B to be 1, because we want strictly positivity on one term for one term, and zeros for the rest, because we want it to be the functional to be non-negative on the others. So linear programming can solve this kind of problem where we demand positivity on a fixed grid of numerical vectors. And so here I show an example where you basically do that. You construct some list of these vectors. And we look for the functional that's positive on them. And then if you do that, then it finds something. But here, okay, here I just, as a test, asked positively only on the scalar part. And then we find something stronger than we found before. And that is, of course, because here I didn't yet include the stress tensor in the spin 2 family. But if you do, then you find the same bound that you found before. So here you find, here I check whether 1.05, whether we can exclude that such a gap. And the fact is that we can exclude it, we find this functional that does it. And yeah, so and what would have happened if you looked for a functional that we saw analytically should not exist, then you find that no solution can be found. And so basically linear programming offers a way to automatically look for such a functional, a positive functional, but you have to discretize your values of delta and L.
Martin, there's a
I
question
didn't
in
get
the
where
chat.
does this 1.03 come out from the automatic computation precisely?
Right, so that's a good question. So I didn't do that here, but you will see it below. So what you would use is, so here I just show, like I try some values and I see that for some it works and for some it doesn't. But if you want to do that systematically, you would realize that in this kind of question where we're asking about a gap, if one point is excluded, then it means that all higher values are also excluded. And if one point is included, it means that all the ones below will also be you will not be able to find any positive functional for the smaller value either. So what you can use is bisection and try a value, and then if it is excluded, half your interval and try again, and below it, and depending on whether it's allowed or disallowed, you go halfway down or halfway up, and so you can quickly converge to the actual value by bisection.
Okay, so I could just do some dichotomy or something like that.
Sorry, what did you say? I think
I could just do some dichotomy. I just cut in half until I guess I get the required property.
Right. And so in fact we do that below when we try a bit further with more components. But this part is just to illustrate that it's possible to check whether a function exists or not.
Okay, thanks.
So in the next part, you can also use, so next I can consider a three-dimensional case or a three-dimensional functional search space. And I consider derivatives. We will see that derivatives, so instead of evaluating just at some points, you can take derivatives around some points, and we'll see that this works better. And it's also a bit more systematic, because by going higher and higher, you are really using Taylor series, and you will see that things will converge, that your bounds at some point, well, that you will change less and less as you increase the number of components. And yeah, so I suggest to basically try to do the same, but with three components, and instead of evaluating at a point, you take derivatives, which is a bit more difficult, a bit more work in the setup, but will be more efficient than just evaluating at a point. And then, okay, we will get a very similar bounds to what you did before. Slightly better, but yeah, this time there is maybe less of a hidden trick in that I tell you that there is a specific combination of Fs that works well.
And which is defined where? Can you point at the line?
What is the exact question?
You said that there's a specific combination that does.
I meant that, so in the first example, I will point at the line. In the first example, I tell you like you can take a two-dimensional subspace, but I also show you that if you do like just randomly one without really thinking about it here, it doesn't give you a good bound. But if you take specifically this combination where you, well, 1/2, 3/5 minus 1/2, 1/3, then you get this much nicer thing.
My question was about the three-dimensional thing.
Right. So sorry, I was comparing what I did.
That was defined.
Right. So for the three-dimensional one, I'm saying you can just take derivatives, and I think so. I took. You can still have some choice, of course, because you can take derivatives. You should find some non-zero derivatives that in some direction, and so there is still some choice. And I think that as long as you take three non-zero derivative terms, that you will be able to get a decent bound. So I was comparing only, I wasn't bringing up the other combination where I gave you this VH. I was saying with three components, I think less of a cheat is required in that I tell you to use a specific good combination to find the.
Okay, I see. Thank you. So when does this method then run out of steam? So what is the execution time here for a three-dimensional case? I mean, why don't you replace 3 by 30 or whatever?
So why I don't do it in this examples, I think, because actually as soon as you go above with 3, you can sort of do a trick so that it still can be plotted in as just an angle again, and that it's still, you can still see it, really visualize what's going on. You can of course go higher, and you should. That's what you do in a real thing, and we will do that in the exercise after that. So yeah, you should do that, and then, well, of course it gets more costly, but it's not a problem yet to go to quite some more components. Yeah. Should I explain more, or should I quiet down so that you can work?
Well, I mean, one extremely practical question that comes up is how much ground you want to cover given the number of sessions that we have allotted to you. So where do you feel that the story should end for today?
So I was thinking that for this week, these exercises that, yeah, the 3, one of which you already consider complete, and then the second one with 3 components, and then another one where we take a bit more components and we show how using linear programming you would do it a bit more structurally, if you had to increase more and more components. So with less of a focus on visualizing, but more of a focus on finding the bounds. And I think that for this week, I would say that this exercise set would be the goal, and then the next week there will be more of a focus on a workflow that you would use in a real Bootstrap setup using. So I will introduce next week then semi-definite programming and the solver that's used to solve these problems, and yeah, additional things like so here we're not optimizing something meaningful, we're just looking for feasibility, but you can also optimize something meaningful, either OPE bound, or you can use this new navigator method. So I was thinking of introducing next week the more real workflow and these kind of tasks. I don't know whether you agree with this, if you want to speed things up or slow things down, or.
Okay, so when you speak about this week, we have you scheduled also for Friday afternoon?
Right.
So for example, right now would now be a suitable place to stop for today, and then people will keep working on this sheet until Friday, and you will show us the fine print.
Right, I agree with that. I think that would be good. That was what I was thinking. So
okay, now let me think carefully before asking the question to the audience. So does anybody not agree on this plan? Let's say you have 3 seconds or 30.
I like that we have some more time until Friday to look at these exercises and maybe ask questions on Friday.
Right.
It's a good idea, I think.
Oh, and there are even a few thumbs up, so that's fine. Okay, great. So let's make this a day. I hope our technicians can cut out the long silent space before placing this session somewhere on the internet. So thank you very much, Marten, and we look forward to working further on this sheet and seeing you again on Friday.
Thank you. I look forward to it.
So I will end the session